Hi there, Mr. Sutton bringing you this lesson on definite integrals, geometric approach. In this one, we're going to be calculating definite integrals, and we'll talk about what that means in a moment, using some simple geometric shapes. So just a few definitions to go through before we get too far into this lesson. This integral symbol, which we've been calling the antiderivative this whole time, can also be called the area under the curve of a function. And by under the curve, we have to be careful how we define that. What we're really talking about is the area between the curve and the x-axis. So there's two kinds of integrals that we can take. One, called an indefinite integral, which just has this antiderivative symbol with nothing else fancy attached to it, is just a general formula for finding the area under the function on any interval. And again, we've also been calling this the antiderivative. Today we're going to look at a different one called the definite integral. So this is the same symbol, but now we have a number in the bottom and the top of this thing. Everything else is the same though. This definite integral is talking about the actual area under f of x on some actual interval from a to b. So just to get a few more definitions out there, a and b are called the limits of integration. A is the lower limit and b is the upper limit of integration. Basically, the starting point of the interval and the ending point of the interval. The actual function inside here, f of x, or whatever it is called the integrand. This is the function that we're about to integrate, to find the area under. And this last little piece here, this dx, is called the differential. For now, we'll just say that this tells us the variable of integration. It does a lot more than that, but that's all we're going with for now. So here we go with our very first definite integral example. When I ask for the definite integral from 2 to 5 of 4 dx, I am asking for the area under y equals whatever this is, 4 in this case, from x equals 2 to x equals 5. So a good way to start these, if you have a graph already drawn, is to shade the area that you're looking for. So we're going from 2, so here's the vertical line at x equals 2, to 5. So we want this rectangular area in between. Well, what is the area of a rectangle? It's base times height. The base in this case is 3. The height is 4. So we're just doing 3 times 4, which is 12. So 12 is the value of the definite integral from 2 to 5 of 4 dx. So this is how you could calculate the definite integral by hand. And there's actually another way of doing it more algebraically that we'll see down the road, but not yet. You can also, it turns out, do this on Desmos. To do this on the graphing calculator, you just need to use int, and plug the information in. So let me just show you that on Desmos. So let's see here. We've got int, and it auto-completes to give you this integral. And then you put in your lower and upper limit, and inside we've got 4 dx, and the minute you write dx, it spits out your answer, which gives us 12. Here's another example. Pause the video and give this one a shot. All right, so this one we want the integral from 0 to 2 of this line. So let me just shade in what we're finding the area of. So we're going from 0 to 2. So this is a trapezoid under here. And for the trapezoid, we've got a few ways we can do this. There's the old MCAS formula, which is 1/2 height times base 1 plus base 2. That typically doesn't get used as much in calculus. One that we use more often than this to show what's really going on is base 1 plus base 2 over 2 times h. Because this shows that what you're really doing is averaging the two bases together and multiplying that by the height. So I tend to use this one a little bit more. So plugging things into that, my two bases, we're going to have 2, and this other one is going to be 8. So the bases are actually just the parallel sides, even if they're, vertical instead of horizontal. And then our height here is just going to be the distance between those two parallel sides, which is 2 in this case. So we've got 2 plus 8 over 2 times 2. These 2's are going to cancel, so this just ends up being 10. Here's an example with an absolute value, which we've already graphed out for you. Give this one a go. All right, so we're going from 0 to 4. So this is a little bit different in that it creates not one, but 2 shaded areas. So this is actually 2 different triangles we need the area of. For both of them, it's just 1/2 base times height. So you could think of this, and you don't have to write this out, but you could think of this as 1/2 base 1 times height 1, and same thing with base 2 and height 2. So for our first triangle, we're doing 1/2 times a base of 2 and a height of 2. And for the second one, we actually have the same base and height. It's just facing the other way. So this is 2 plus 2, which ends up being 4. Here's another example for you to try out. Give this one a shot, and then try this out on the calculator just to make sure that your answer matches the approved value. All right, let's enter this on the calculator. So we're doing Math 9, going from -1 to 3. We have negative 2x inside here, and x for the differential. And that comes out to -8. Did you get -8? Good if you did. If you didn't, if you got, for example, 10, then let's take a look and see what might have gone astray for you. So we've got -1 is one endpoint, 3 is the other. So we have two triangle areas again, just like the last problem. However, this is a little bit different. So our first triangle area, we've got 1/2 times 1 times 2. That's fine. For the next triangle area, you might be saying, okay, this should be 1/2 times 3 times 6. However, you're a little bit off. It turns out that area under the x-axis is considered negative area. Way you could think about it is you've essentially got a negative height going on here, which is kind of weird geometrically, but that's how these integrals work. So we need to do minus 1/2 3 times 6. So this then is going to be 1 minus 9, which comes out to -8. So we've been doing straight functions up to this point. We're going to do one that's a little curvier now. Pause the video and give this one a shot. All right, so we're going from 0 to 3. That's going to be just this region here. And this is a quarter circle. So in order to find this area, we first need the area of a whole circle, pi r squared. Now we just want a quarter of this, so 1/4 pi r squared. And this circle is under the x-axis, so we know this is going to be negative area from that last example. Okay, well, all we need to do at this point is figure out the radius. The radius is 3, so this is -1/4 pi times 3 squared. That's going to be 9 pi over 4, all negative, for that area. On this problem, we're trying to find the area under this semicircle, so we'll do this one together. So we have this shaded area here that doesn't really follow a typical shape. There's no MCAS formula for whatever this shape is called, but it is made up kind of sort of shapes that we do know. For example, we could think of this as being a rectangle with a semicircle carved out of it. So sometimes it's easier just to subtract the area that you don't want from shapes that you already know. So we have basically a rectangle minus a semicircle. Area of the rectangle, that's a base times height sort of deal. We have a base of 4 times a height of 3. And for the semicircle, in general, 1/2 pi r squared. The r is 2 in this case, so that's 1/2 times pi times 2 squared. And we could leave it like this, or if you want to simplify, we can call this 12 minus 2 pi. So that'll just about do it for this one. Till next time, Mr. Sutton signing off.